The research proposes Heads-Up Experience, HUX, an AI system designed to enhance human-environment interaction. By tracking eye gaze, analyzing the environment, and interpreting verbal contexts, HUX captures and enhances multimodal data, providing holistic context interpretation and memory storage in real-time task-specific situations. This comprehensive approach enables more natural, empathetic, and intelligent interactions between the user and HUX AI, intended for deployment in smart glasses and extended reality headsets. The system aims to become a personal and useful AI companion for daily life, integrating digital assistance with enhanced physical world interactions. This technology has the potential to revolutionize human-AI collaboration in both personal and professional spheres, paving the way for the future of personal smart devices. The paper highlights the concept of HUX AI and its capabilities through a figure and a video link, demonstrating its potential to bridge the gap between current personal smart devices and human-environment interaction. The paper discusses the evolution of human-computer interaction, HCI, to human-computer environment interaction, HCEI, focusing on enhancing the input and output modalities in personal smart devices, PSD. It introduces the HUX AI, designed to realize HCEI principles, and its deployment device, the HUX device, which includes custom setups, smart glasses, and extended reality headsets. The HUX AI aims to understand and interact with the user's environment, making it a key component in next-generation PSD. The paper also defines task of interest, objects of interest, OOI, events of interest, EOI, real-time video analyzer, multimodal context processing, and region of interest, ROI. These concepts are crucial for understanding how the HUX AI processes and interacts with the user's environment. For instance, the real-time video analyzer uses computer vision models to detect OOI and EOI within a video feed, providing insights into the sequence of events and their impacts. Moreover, the paper highlights the importance of multimodal context processing, which involves feeding multimodal data into a large language model, LLM, to generate context-aware answers. This process is critical for the HUX AI to understand and respond to the user's needs effectively. The paper concludes by emphasizing the significance of improving HCI to HCEI in PSD, enabling humans to interact more efficiently with both digital and real-world environments. The HUX AI and its associated technologies have the potential to revolutionize how we use and interact with PSD, making them more intuitive, responsive, and integrated into our daily lives. Transformer-based language and vision models have demonstrated human-like contextual understanding, enabling the creation of a user-centric AI system that enhances human-computer environmental interaction, HCEI. By deploying these models in extended reality headsets or smart glasses, the system can align its perception with user perception data, reducing friction in human-computer interaction, HCI, and minimizing the need for human articulation. The paper focuses on designing subprocesses that serve unique purposes and integrating them to assemble a prototype for a HCEI system. This work aims to build a PSD with integrated AI, moving beyond the current graphical user interface, GUI-centric approach in PSD. The paper is organized into sections, including a comparative analysis with existing literature, problem statement, HUX AI architecture, applications, experiments, discussion, limitations, and future works, and concluding remarks. The comparative analysis delves into selective attention theory, video processing, merits of visual enhancement in extended reality, embodied AI, and multimodal HCI. Selective attention theory, a critical cognitive process, allows individuals to focus on specific stimuli while ignoring irrelevant information. Various models have been proposed, including Broadbent filter model, Treisman attenuation model, Deutsch and Deutsch late selection theory, and Levy load theory, which have refined our understanding of human information processing. Addressing the limitations of selective attention is essential for enhancing safety, improving decision-making, and increasing efficiency in various environments. By understanding human information processing, the HUX AI system can be designed to reduce cognitive load, allowing individuals to focus on their primary tasks effectively, and improving overall productivity. The integration of transformer-based models and extended reality headsets or smart glasses can create a more intuitive and efficient HCEI system, paving the way for innovative applications in various fields. The HUX AI is a novel approach to enhancing human awareness through real-time human-AI collaboration, leveraging insights from selective attention theories. It observes objects and events of interest in the environment, providing additional environmental awareness for better informed decision-making. The HUX AI is context-aware, determining the relevance and importance of information. In video processing, the HUX AI uses events of interest, EOIs, based frames, leveraging deep learning models such as YOLO to analyze real-time video and extract EOIs using objects of interest, OOIs. This method enhances the signal-to-noise ratio, reducing computational cost due to the vision language model, VLM, thereby increasing efficiency. Visual enhancement in extended reality is achieved through holographic labeling using AR algorithms and deep learning-based algorithms. Models such as YOLO play a crucial role in extracting EOIs in real-time video analysis and OOIs labeling in the scene, offering dual merits. This concept is extended by feeding the enhanced scene perception to a VLM, allowing the HUX AI to see what the user sees in a task-specific scenario. Embodied AI systems such as Humane Pin and Rabbit R1 utilize VLMs to enhance human-computer interaction, HCI. The HUX AI uses VLMs to understand dynamic scenes in HCI environments, similar to the approach demonstrated in AutoRT, where VLMs are used for scene understanding and grounding in robotics. Multi-modal HCI is also explored, building on advancements in gaze-facilitated information querying systems. The HUX AI extends the concept of multimodal querying into a dynamic and real-time task-specific environment, incorporating active change detection, real-time environmental adaptation, and personalized context memory. This approach addresses identified challenges, particularly in enhancing human-AI collaboration and improving decision-making processes. Here is the combined summary. The research aims to resolve query ambiguities and adapt to user situational context in human-computer environment interaction, HCEI, by integrating multimodal features and gaze-enhanced information retrieval systems. This work contributes to the evolving landscape of HCEI, offering new possibilities for responsive and context-aware systems. In contrast to previous work, which is not real-time and involves 4 rounds of questioning, this research extends the approach by deploying it in a real-time test environment with continuous changes, allowing for dynamic testing with multiple questions involving different modalities within the same environment. The problem statement lies in the limitation of personal digital assistants, PSDs, in aiding humans in real-world scenarios, confined to digital expertise and specific domains. The goal is to create a PSD that enhances user productivity, decision-making, understanding, and task-specific scenarios in diverse environments, ultimately boosting productivity in real-world environments. The future utility of a general-purpose AI is decided by the number of domain-specific tasks in which human-AI collaboration is possible. Figure 2 illustrates the capability of AI-enabled devices, showcasing a domain-specific model optimized for precise tasks and a generalist model offering broad language understanding and generation. HUX AI integrates a generalist base with modular, task-specific layers for flexible and specialized applications. The HUX AI agenda, outlined in Table 1, aims to ensure expertise in primary tasks, promoting regular use, and proficiency in multiple daily tasks, enabling broad applicability throughout the day. The agenda envisions wearables functioning as a companion expert, enhancing user capabilities across various daily tasks. Here is the combined summary of pages 11 and 12. The AI utility of a device is measured by the number of domains it can operate in, multiplied by its performance in each domain-specific task. This utility is critical in determining the necessity of the AI in various tasks and its usability in diverse environments. The HUX AI integrates a generalist base with modular and task-specific layers, enabling flexible and specialized applications. In a task-specific environment, 3 key properties are observed: objects of interest, OOIs, events of interest, EOIs, and environmental context, EC. OOIs are task-specific sets of relevant objects or entities, which may have varying levels of importance or priority. EOIs are task-specific sets of relevant actions or phenomena, including both expected and unexpected events. EC refers to the relevant background information and conditions of the task environment, influencing how OOIs and EOIs are perceived and interpreted. The desired features of AI for varied usability include spatial and temporal real-time scene understanding in a task environment. The HUX AI tracks only EOIs and OOIs confined to a task environment, efficiently computing and clarifying task context while avoiding unnecessary spatial and temporal information. Additionally, the AI should understand user perception by generating the region of interest, ROI, using eye gaze data and enhancing visual perception using AR or deep learning algorithms for object and scene labeling. Contextual interaction using multimodal data enables the AI to assist users with real-time queries, suggestions, and answers. Furthermore, the AI should understand, remember, and recall multimodal interaction, recalling contextual and event information and patterns in an interaction session. Finally, the future scope of the HUX AI includes multimodal outputs and actions. The heads-up experience HUX system integrates user perception and optimizes it for human-AI collaboration, handling real-world or digital environments. This approach narrows the lines between human and AI capabilities, enhancing the overall user experience. Here is a combined summary of pages 13 and 14. The heads-up experience HUX integrates artificial intelligence, AI, into smart glasses, extending the concept of a traditional heads-up display, HUD, by emphasizing an immersive, interactive, and multimodal interface. This AI system, also referred to as HUX AI, enhances user engagement with their surroundings in a dynamic and contextually aware manner. By consolidating functionalities typically managed by separate devices, HUX AI eliminates the need for smartphones and other gadgets, allowing users to perform a wide range of actions, access information, and interact with their environment directly through the heads-up interface. The HUX AI architecture, depicted in Figure 3, consists of integral components that manage data flow, processing, and modalities. Input data modes are converted to text captions and descriptions, integrated by the multimodal context processing engine using a prompt architecture. The creation of a new voice file triggers a multimodal context processing episode, collecting the latest scene captions stored in the last and only used LiU stack and retrieving the latest ROI caption whose origin image is created simultaneously with the speech audio file. The multimodal context processing engine receives textual representations of all possible input modalities, processes the data, and returns the output to the user. This engine operates in a dynamic environment, where the user's goal is to accomplish a task of interest. The HUX AI system provides processed perception input to the user, receives user inputs, and generates outputs. The core models used in the system include a vision language model for image captioning, a large language model for multimodal context processing, and task-specific perception models such as YOLO and printed circuit board defect detection for identifying objects of interest, OOIs, and elements of interest, EOIs. The system's modalities include user speech input, eye gaze information, and other inputs that trigger multimodal context processing instances. These components work together to provide an immersive and interactive experience, enhancing user engagement with their surroundings. The HUX AI architecture, as depicted in Figure 3, is a multimodal system that processes data through various stages including origin, processing, context processing, and output generation. This architecture utilizes a LiU stack, or last and only used stack for efficient data handling. Page 16 details the components of the HUX AI system, including a real-time video analyzer, vision language model, large language model, and multimodal contextual memory. The real-time video analyzer detects task-specific events of interest, EOI, and out of interest, OOI, in real-time video feeds, extracting frames as needed. The vision language model converts input images into captions when required. The large language model serves as a multimodal data context processing engine and is also used for generating language outputs. The multimodal contextual memory stores contextual multimodal data for long-term retrieval. Figure 4 illustrates the temporal flow of frames from a real-time video feed, with green boxes indicating filtered EOI frames detected by the real-time video analyzer. These frames are sent to the vision language model for captioning, and the event data combined with image captions are then processed sequentially with metadata. The data from selected frames triggered by certain events are updated in the context window. EOIs can be obtained from real-time video of the environment through changes in the number of objects of interest, changes in object behavior, or custom-defined events specific to the application domain. This includes detecting gestures, actions, or environmental changes. Overall, the HUX AI system is designed to efficiently process and analyze multimodal data in real time, providing a robust framework for various applications requiring advanced AI capabilities. Here is a combined summary of pages 17 and 18. Figure 4 illustrates the expected real-time event-based video context processing using vision language models, VLMs, for detected events of interest. In contrast, Figure 5 highlights the reality of real-time event-based video context processing, where some events are missed due to the computation time of the previous frame. The VLM computation time is spent processing the previous frame, resulting in subsequent events of interest being missed until the VLM is freed. Once the VLM completes processing a frame, the events of interest, EOIs, are exported as frames to be processed by the VLM, and the event data from the real-time video analyzer is sent to the context processing engine to reconstruct the temporal scene textually. This hybrid approach enables the context processing engine to understand occurrences in real time while saving significant computing and processing time. Notably, during VLM processing of a frame, multiple frames might get classified as EOIs. After the VLM completes processing the current frame, the middle frame is skipped over to focus on the latest frame, as depicted in Figure 5. This approach ensures that the real-time video analyzer provides essential event data, including counts, to the context processing engine. By adopting a hybrid approach, the system can efficiently process real-time video data, leveraging the strengths of both VLMs and context processing engines. This architecture enables the system to reconstruct the temporal scene textually, providing a comprehensive understanding of events in real time. The paper presents a hybrid approach for real-time event-based video context processing using visual language models, VLMs, to extract information from detected events of interest. This method leverages the merits of both image and video processing to enhance user perception and task-specific scene understanding. The authors highlight the importance of identifying and processing events of interest, EOIs, in real-time video streams, which can be challenging due to the complexity of scenes and the need for real-time computation. The proposed approach utilizes a real-time scene analyzer to identify EOIs and then applies this information to enhance user perception visually. This is achieved through task-specific scene enhancement, where the same computer vision model is repurposed to filter out events and annotate the scene image feed with objects of interest, OOIs, relevant to the user's task. This approach offers several benefits, including improved task-specific selective attention, awareness of the scope of task-specific OOIs, modularity to handle different tasks, adaptive attention allocation, attention restoration, and selective ignorance cultivation. The authors also discuss limitations and future work, such as the potential for improved techniques for mental recovery and focus renewal in the scene. They emphasize the importance of dynamic shifting of focus based on changing environmental priorities and the need to disregard non-essential information for the task intentionally. Overall, the paper presents a novel approach for enhancing real-time video context processing and user perception, with significant implications for various applications in computer vision and artificial intelligence. The paper discusses the modularity of task-specific computer vision models for enhancing user visual scenes in augmented reality applications. Figure 7 illustrates how different computer vision models, denoted as Task 1, Task 2, Task 5, are used to detect and label objects of interest, OOIs, in various scenarios. This task-specific enhancement is facilitated by agentic behavior, which allows the system to understand context and decide when to utilize specific models without explicit user input. The user's visual scene is enhanced by the chosen model, providing a visual aid through labeled OOIs. The same image is also processed by the visual language model, VLM, to align with the user's perception. This process enables the system to understand and empathize with the user's visual experience. Text instructions and annotations unique to each task are passed to the VLM for better scene interpretability and to the language model, LLM, for enhanced context understanding. Consequently, the user can engage in conversations with the LLM regarding the scene. The paper also outlines the eye gaze processing pipeline, as depicted in Figure 8. This figure demonstrates the parallel and interdependent nature of gaze and scene processing. Colored images indicate frames where new objects of interest are observed, while subsequent black and white frames do not require VLM processing for image captioning, thereby demonstrating computational efficiency. When a new object of interest is detected, the corresponding frame is sent to the VLM for image captioning, and the region of interest, ROI, from the scene image, along with eye gaze data, is extracted and processed. The user's utterances are captured and converted to text using OpenAI Whisper, further enriching the interactive capabilities of the augmented reality system. The process of eye gaze processing in parallel with scene processing is illustrated in Figure 8. Eye gaze data obtained from wearable hardware, including gaze coordinates and the perimeter of the gaze area, is used to segment the region of interest, ROI, from the overall scene. This ROI is then used by the vision language model, VLM, to generate text inferences. The scene image itself is also passed to the VLM for image captioning. The multi-modal context processing engine translates this data into textual form, combining it with the VLM's outputs. This combined data is then stored in a structured multimodal memory format, which can be retrieved later using contextual cues through techniques like retrieval augmented generation, RAG. Figure 9 demonstrates the implementation of this process, where the scene image is sent to the VLM for captioning and ROI processing. The ROI is extracted using various inputs such as verbal specifications or eye gaze. This ROI is then sent to the VLM for further captioning. User context is extracted from conversation and combined with the multimodal data to generate keywords, phrases, and other contextual cues. Figure 10 shows the data structure of a multimodal contextual memory, highlighting its relationship with other memories. The data types include the object of interest, OOI, identified using YOLO, and the multimodal data comprising image, text, and conversation context. This structure enables efficient retrieval and utilization of contextually relevant information for future interactions. The research discusses the development of a multimodal contextual memory pipeline, focusing on efficient data storage and retrieval. It introduces a novel data structure for storing images, captions, and contextual information. This structure enables the system to minimize computation costs during future queries by generating probable user queries through a language model. The pipeline includes modules for scene and object captions, speech input, meta-information, and LLM-generated content. The system's capabilities are demonstrated through its application in solving the selective attention problem in real-time human-environment interaction. This involves the AI paying attention to tasks outside the scope of human selective attention, highlighting the potential benefits of this technology in enhancing human-AI interaction. Enhanced situational awareness is facilitated through the HUX AI system, enabling improved detection of subtle environmental cues or threats in complex scenarios. Additionally, cognitive offloading is achieved by monitoring less salient task elements, freeing up human cognitive resources for higher-level decision-making. Furthermore, the AI system provides enhanced multitasking support in complex scenarios requiring attention to multiple subtasks, managing parallel information streams more effectively than humans. In the spatial and temporal scene recall experiment, two scenes are presented, Scene 1 with 5 demo videos of 30 seconds each, and Scene 2 with 1 demo video of 13 seconds. The scenes feature fruits placed in a dark background, with some fruits removed and replaced in the background. The HUX AI computer vision analysis is compared to manual video analysis, showing general alignment but some discrepancies. The AI system identifies the highest variety of fruits at specific timestamps, while manual analysis identifies it at a different timestamp. Both methods agree on the absence of a consistent pattern in adding or removing fruits and the dominant presence of bananas. The system utilizes selective real-time data computation, storing all data without real-time computing and computing only when necessary. Only frames with events of interest, EOIs, are computed in real time due to resource and time constraints. In the task-specific scene perception experiment, a multimodal task-specific scene perception is demonstrated using AR algorithms and deep learning computer vision algorithms. The visual language model, VLM, is used in image captioning of the enhanced scene. The experiment scenario involves an engineer examining a printed circuit board, PCB, using a computer vision model to find defects. The model is triggered automatically based on user perception, leveraging LLM-based agentic behavior. The workflow is described in Table 2, where the user requests help with visual identification, and the agent visually inspects the PCB, providing a response. The scenario begins with a user inquiring about the components on a printed circuit board, PCB, and identifying any defects. The agent uses the PCB-HUD tool, which has a PCB defect detection model, to analyze and infer defects in the circuit. 3 defects, all mouse bites, are identified and described by their spatial locations verbally using visual language modeling, VLM. When the user seeks more information on these defects, the agent explains what a mouse bite defect is, bridging knowledge from the task scene enhanced by the task-specific computer vision model and large language models' trained knowledge. The user then checks the agent's memory, asking how many defects were seen, and the agent confirms 3 defects and reiterates their locations. The interactions are summarized in Table 2, showcasing the conversation between the user and the agent. The agent uses the PCB model to find defects in the circuit, receiving a labeled image that indicates 3 mouse bite defects. These defects are explained as imperfections or damage to the copper foil on the circuit board, potentially causing electrical connections to fail. The agent maintains accurate knowledge throughout the conversation, correcting any potential misunderstandings, such as when the user asks about flowers, clarifying that they were discussing a PCB, not flowers. The research discusses the creation of multimodal contextual memory, focusing on a real-life scenario where a user asks the HUX AI system to remember a new engineer, a mom. This involves capturing a scene image and extracting relevant information using conversation context. Figure 12 illustrates this process, showing the scene image and the region of interest extracted by the agent. Table 3 provides a detailed demo of multimodal contextual memory storage for a mom, highlighting attributes such as his appearance, the setting, and the objects in the scene. The context includes a mom's position in the lab, wearing a yellow t-shirt with the word "Dill" written on it, and his friendly demeanor. The background details the lab's workspace, with shelves filled with boxes and electronic components, suggesting a tech or electronics workshop. The summary emphasizes the importance of this multimodal approach in creating contextual memories, which is crucial for AI systems to understand and recall complex scenarios. The research on HUX AI focuses on selective attention, drawing inspiration from psychological assessments. It explores the ability to pay attention to multiple things the user is not, aiding in real-world stochastic situations. The system helps verbal recall of objects by having conversations about overlooked items. The experiment setup involves a dark background with objects of interest as fruits, and the system's observational capabilities are restricted to increase the signal-to-noise ratio. The goal is to dynamically change the environment by adding or removing fruits, while the user interacts with the AI, asking questions about the environment using eye gaze. The test aims to mimic any environment, and promising results could be applied to other environments. The experiment uses a single user, and the system's usefulness is tested through various types of questions, including those that involve multiple modalities. The hardware used includes 3 independent systems networked together for computation. The research paper presents a multi-system architecture for real-time event detection and response, comprising 3 interconnected systems: System 1, System 2, and System 3. System 1, the primary computer, is equipped with an Intel Core i7 13th General CPU, 12 GB VRAM, and an NVIDIA RTX 4070 Ti graphics card. This system is responsible for collecting user speech input, converting it to text, and capturing the user's eye gaze using a Tobii Eye Tracker 5. The eye gaze coordinates are converted to region of interest, ROI, images, which are then processed in real time. The system also captures the scene using a camera and detects events using a model that runs on the computer. System 2, the main hub, has an Intel Core i914th General CPU, 32GB RAM, and 16GB VRAM. This system receives ROI gaze images and speech-to-text converted utterances from System 1. The ROI gaze images are passed through a vision and language model, VLM, to generate image captions whenever there is new speech input. The system collects and stores multimodal data in real time, which is then fused with a large language model, LLM, prompting strategy. The LLM generates a text answer, which is converted to speech output. System 3, responsible for scene processing, has an Intel Core i7 13th General CPU, 32GB RAM, and 12GB VRAM. Due to the high video memory requirements of the VLM, scene processing is outsourced to this computer. The system generates a text description of the significant event scene, which is then used in the overall event detection and response pipeline. The hybrid approach, depicted in Figure 5, was not used in this implementation. Here is a combined summary of pages 37 and 38. The Human User Experience (HUX) AI system receives raw eye of interest (EOI) frames from System 1, processes them, and sends them to System 3 as image captions in real time. Due to deployment limitations, the system is divided into 3 parallel systems that act in synchronization to utilize the total capacity. Notably, multimodal contextual memory was not integrated into this pipeline but tested separately. In user interaction with the AI, the user presses and holds the spacebar on a QWERTY keyboard to input voice commands. The system captures the voice input until the spacebar is released, and the current gaze image is captured simultaneously. The EOI frames extraction operates independently, only changing when there is a change in the environment. The user then waits for the answer, processed by the pipeline, without the ability to interfere or pause the HUX AI response in this prototype version. During trial user interaction runs, errors were noted, including speech-to-text conversion errors and instances where the user's gaze was outside the scope of the scene environment. Additionally, general problems identified in the large language model, LLM, conversation include hallucination and forgetfulness. The multimodal context processing prompt architecture is designed to answer questions based on previous responses and new multimodal information. The architecture consists of 4 components: a general description of the user environment, the user's gaze-based region of interest, ROI, description, the speech-to-text converted contextric user utterance, and a relevant and precise answer to the user's query. The experimental demonstration section presents example user queries that can be asked to the implemented system, along with the origin or source of data that the multimodal context processing can use to answer the queries, as shown in Table 4. The HUX AI system, designed to enhance human perception and reduce cognitive load, utilizes real-time scene analysis and interactive questioning. This is achieved through a human-AI collaboration, where the AI processes multimodal context from user prompts, gaze, and speech. Table 4 illustrates examples of user prompts and the corresponding multimodal data used to answer them. The experimental setup, as shown in Figures 13, 14, and 15, involves a user seated in front of a display showing the real-time scene feed. A webcam captures the live scene, and a laptop provides supportive material for the user to test out the capabilities and kinds of queries to be asked. The user utters queries while holding the spacebar pressed, during which gaze data from the hardware is also extracted. The HUX AI's prompt architecture is responsible for multimodal context processing, as shown in Table 4. This system can overcome issues humans face in selective attention by retrieving data from HUX AI memory when humans prompt it in real time. This feature reduces the cognitive load on the user and helps improve the quality of life of humans. Although the current prototype has latency issues, this can be tackled in future versions of the HUX AI. The HUX AI enhances and perceives the scene to aid human perception and ask specific questions and answers regarding the enhanced visual feed. Improving visual information and facilitating interactive questioning helps humans by offering contextual insights, clarifying visual details, and enabling informed real-time decision-making. The current method for storing memory is restricted to singular modalities like storing images, texts, or voices in real time. The HUX AI demonstrates how to store and process multimodal context, providing a more comprehensive understanding of the scene. This technology has the potential to significantly enhance human perception and decision-making capabilities in various real-world applications. The paper discusses the development of an AI system capable of creating multimodal contextual memory and retrieving it through contextual cues. This is achieved by integrating multiple data types, enhancing memory recall and decision-making based on interconnected data. The system's efficacy is demonstrated in a series of experiments involving human-AI interaction within a complex environment. Figures 14 and 15 depict the experiment setup from behind and the complete scene, respectively. The setup showcases the AI's ability to capture and store scene captions in real time, facilitating accessible and intuitive information retrieval. However, the current implementation has limitations. For instance, more environments need to be tested to determine where users find them useful. Additionally, environments with different objects and complicated events of interest must be explored. The stack implementation of storage of scene captions leads to loss of scene data in real-time interaction. Future works include assessing multimodal memory retrieval capabilities in large-scale data, considering privacy limitations. The authors also plan to increase the complexity of the environment by introducing different events and objects of interests. Furthermore, they intend to conduct further studies on human-robot interaction with HUX AI and explore wearable robotics as a form of human-AI collaboration. The Heads-Up Experience HUX artificial intelligence system is designed to revolutionize personal smart devices by enhancing human-computer environment interaction, HCEI. It leverages its ability to detect changes in the user's environment and interpret user intentions through a multimodal interface. This system can be integrated with various technologies such as wearable robots, drones, smart appliances, and GUI navigation to provide seamless control and interaction. In the context of wearable robots, HUX AI can facilitate communication and manipulation tasks when integrated with a snake robot or manipulator. The system can also collaborate with drones to aid human-environment interaction, performing additional perceptions and manipulations. Furthermore, HUX AI can be connected to smart devices, enhancing user interaction by interpreting and acting on user intentions. Moreover, HUX AI can navigate GUI environments, such as external computer screens, smartphones, smart devices, and VR screens, by interacting with UI elements and events of interest. This capability allows it to accurately interpret user intentions and facilitate a frictionless HCEI, enhancing human-AI collaboration. Additionally, HUX AI can be customized to process multimodal data according to each user's unique needs, making it an empowering tool for differently challenged users. Its ability to store contextual, multimodal memories enables the fusion of diverse data types, greatly aiding creative endeavors such as brainstorming. By integrating and synthesizing varied information, HUX AI can support more holistic and imaginative problem-solving processes. Here is a combined summary of pages 45 and 46. HUX AI is a novel framework designed to facilitate seamless human-AI collaboration across various scenarios, revolutionizing the way humans interact with computers and their environment. This framework incorporates a sophisticated multimodal interaction framework, leveraging eye gaze, scene analysis, and speech input to enable more effective and intuitive interactions. By doing so, HUX AI sets the stage for future advancements in personalized intelligent technologies. The concept of HUX AI draws inspiration from various sources, including language models that have demonstrated few-shot learning capabilities, and large language models that have achieved adult human performance on higher-order theory of mind tasks, 2. Other influential works include the Rabbit R1 AI device, 3, and the Humane AI Pin, 4, which, despite their limitations, have contributed to the development of human-machine interfaces. The concept of attention is critical in understanding the HUX AI framework. Research on selective attention, 58, highlights the importance of perceptual load in filtering out irrelevant information. This concept is particularly relevant in the context of object detection, as demonstrated by the Yolov-7 algorithm. 10. Furthermore, the introduction of GPT-4o-9 has also influenced the development of HUX AI. The framework has applications in various domains, including mixed reality, as demonstrated by the Microsoft HoloLens 11, 12, and robotics, as shown by the AutoRT embodied foundation models 13. Additionally, the concept of gaze-facilitated information querying, as explored in GVoila 14, has also contributed to the development of HUX AI. Overall, HUX AI represents a significant advancement in human-AI collaboration, enabling more sophisticated and personalized interactions between humans and machines. The pages discuss advancements in multimodal models, particularly focusing on the gap between current open-source suites and commercial models. The authors highlight the need for scaling up vision foundation models to align with generic visual linguistic tasks. They also emphasize the importance of object detection models and datasets for achieving this goal. The concept of retrieval-augmented generation for knowledge-intensive NLP tasks is introduced as a key methodology. Furthermore, the role of aerial grippers in robotics and visual language models for GUI agents is discussed. The pages conclude by highlighting the need for synergy between different technologies to achieve significant advancements.